Mars hangs in our sky like a promise or a dare, millions of kilometers away, constantly moving, utterly indifferent to whether we ever set foot on it. Getting there is brutal. Coming back is worse. The total journey? One of the longest, most dangerous trips any human will ever take. Today, we're breaking down exactly how long this odyssey lasts, and why once you leave Earth, there's no coming home early. If you're someone who loves exploring the mysteries of space and understanding our place in this vast universe, hit that subscribe button and give this video a like. It really helps us reach more curious minds like yours. Now let's get started. Standing on Earth and looking at Mars in the night sky, you might think the distance between us is fixed, like two houses on opposite sides of a street. But that couldn't be further from the truth. Both planets are constantly moving, orbiting the Sun at different speeds and along different paths. Earth completes its orbit in 365 days, 1 year as we know it. Mars, being farther from the Sun, takes significantly longer, 687 Earth days, or roughly 1 year and 10 months. This difference in orbital periods means that the distance between Earth and Mars is constantly changing, stretching and shrinking as both worlds circle our star. At their closest approach, which astronomers call opposition, Earth and Mars can be as near as 54.6 million kilometers apart. That's about 34 million kilometers if you're thinking in those terms. Picture that for a moment. 34 million kilometers. It sounds impossibly far, and it is, but in the grand scheme of the solar system, it's practically neighbors dropping by for tea. At their farthest, when the two planets are on opposite sides of the Sun in what's called conjunction, they can be separated by as much as 401 million kilometers. That's roughly 249 million kilometers. The distance between our two worlds can vary by more than 7 times depending on where each planet happens to be in its orbit. This cosmic dance between Earth and Mars creates what space mission planners call launch windows. These are specific periods when the alignment of the planets makes a journey to Mars most efficient. You can't just hop on a rocket whenever you feel like it and head to Mars. You have to wait for the right moment when the planetary positions allow for the most fuel-efficient trajectory. These ideal launch windows open up approximately every 26 months, specifically every 780 days, which is the synodic period of Mars. Miss your window, and you're waiting over 2 years for the next opportunity. The trajectory that spacecraft use to travel between Earth and Mars is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who first described it back in 1925. This isn't a straight-line path. Instead, it's an elegant elliptical arc that takes advantage of the orbital mechanics of both planets. Think of it like throwing a ball to someone running on a track. You don't aim for where they are now, you aim for where they're going to be. The spacecraft launches from Earth and follows a curved path through space, arriving at the point where Mars will be months later. It's a cosmic game of interplanetary catch that requires incredibly precise calculations. Using a Hohmann transfer orbit, the typical travel time from Earth to Mars ranges from 6 to 9 months, depending on the specific positions of the planets during that particular launch window. Most missions aim for somewhere around 7 months. 7 months. Let that sink in for a moment. That's longer than a school semester. It's about as long as a human pregnancy. Imagine being confined in a spacecraft, hurtling through the void of space for 7 months, knowing that Earth is getting farther and farther behind you with each passing day. NASA's Perseverance rover, which launched in July of 2020 during one of these optimal windows, took exactly 7 months to reach Mars, landing in crater Jezero in February of 2021. The Curiosity rover before it launched in November of 2011 and arrived in August of 2012 after an 8.5-month journey. The Mars Science Laboratory mission that carried Curiosity traveled approximately 563 million kilometers to reach its destination. Not the direct distance between the planets, but the actual curved path through space. Now here's where things get really interesting. The journey to Mars is only half the story. Once you arrive, you can't just immediately turn around and come home. Remember how I mentioned those launch windows that open every 26 months? The same principle applies in reverse. After arriving at Mars, astronauts would need to wait for the planets to realign into a favorable position for the return journey. This waiting period on the Martian surface would last anywhere from 15 to 18 months. Yes, you read that right. Over a year stranded on another planet, waiting for the cosmic alignment that makes the journey home possible. During this extended stay, astronauts wouldn't just be sitting around counting Martian sunsets, although they would witness approximately 540 of them. They'd be conducting scientific research, maintaining their habitat, growing food, exercising to combat the muscle and bone loss that occurs in Mars's lower gravity, which is only 38% of Earth's, and constantly monitoring systems that keep them alive in an environment that is fundamentally hostile to human life. The atmosphere on Mars is 95% carbon dioxide, with an average surface pressure less than 1% of Earth's. You couldn't breathe there for even a moment. The average temperature hovers around -63 degrees Celsius or -81 degrees Fahrenheit, though it can swing wildly from a relatively balmy 20 degrees Celsius at the equator during midday to a frigid -125 degrees Celsius at the poles during winter. After waiting through those 15 to 18 months on Mars, the return window finally opens. The journey back to Earth takes another 6 to 9 months, following another Hohmann transfer orbit, but in the opposite direction. This means the absolute minimum round-trip mission to Mars, including travel time and the mandatory surface stay, would last approximately 21 to 24 months. That's nearly 2 years. 2 years away from Earth. 2 years away from your family, your friends, blue skies, breathable air, and the comforting tug of Earth's gravity. 2 years where the planet you call home is just another bright dot in an alien sky. But here's the reality check. The 21 to 24-month estimate is the absolute best-case scenario, and space missions rarely go exactly according to plan. Mission planners typically budget for 30 to 36 months, that's 2.5 to 3 years, to account for contingencies, equipment malfunctions, medical emergencies, or the need for additional time on the surface to complete scientific objectives. NASA's current designs for human Mars missions are built around this 30 to 36-month time frame. 3 years. Think about where you were 3 years ago and how much has changed in your life since then. Now imagine spending those 3 years in a tin can, millions of kilometers from home. The challenges of such an extended mission go far beyond just marking time on a calendar. Human bodies weren't designed for long-duration spaceflight. In the microgravity environment of deep space, astronauts lose bone density at a rate of about 1 to 2% per month. That's 12 to 24% bone loss over the course of a year. Muscles atrophy without the constant resistance that Earth's gravity provides. The heart, no longer working as hard to pump blood against gravity, can shrink and weaken. Vision problems can develop as fluids shift toward the head in weightlessness. The immune system becomes compromised, making astronauts more susceptible to infections. Then there's radiation. Oh, the radiation. On Earth, we're protected by our planet's magnetic field and thick atmosphere, which shield us from the constant bombardment of cosmic rays and solar particles streaming through space. Once you leave Earth's protective bubble, you're exposed to radiation levels that would be unthinkable on our home planet. During the journey to Mars, astronauts would be exposed to approximately 300 millisieverts of radiation. That's equivalent to getting a full-body CT scan every 5 to 6 days for 7 months straight. For comparison, the average person on Earth receives only 2 to 3 millisieverts per year from natural background radiation. The long-term health effects of this exposure include increased cancer risk, potential damage to the central nervous system, and possible impacts on cognitive function. Mars itself offers little protection. Unlike Earth, Mars has no global magnetic field to deflect charged particles, and its thin atmosphere provides minimal shielding. Surface radiation levels on Mars are about 40 to 50 times higher than what we experience on Earth. During the 15 to 18-month surface stay, astronauts would need to live in heavily shielded habitats, possibly using Martian soil piled on top of their modules to provide additional protection. Even then, they'd accumulate significant radiation exposure. Some mission concepts propose using lava tubes, underground cave systems created by ancient volcanic activity as natural radiation shelters. These geological features could provide the thick rock barrier needed to protect human occupants from the relentless cosmic rays. The psychological challenges might be equally daunting. Imagine being confined with the same small group of people, perhaps 6 to 8 crew members, for 3 years, knowing that if serious conflicts arise, there's nowhere to go, no escape, no possibility of early return. Communication with Earth becomes increasingly difficult as the distance grows. At Mars's closest approach, a radio signal traveling at the speed of light takes about 3 minutes to cross the gap. At farther distances, that delay stretches to 22 minutes. This means every conversation with mission control or loved ones back home has a lag time of 6 to 44 minutes round trip. You can't have a real-time conversation. You can't call home when you're feeling lonely or scared. Every message is like sending a letter and waiting for a reply that might not come for nearly an hour. This isolation is profound in ways we're only beginning to understand. Earth would shrink to a pale blue dot in the Martian sky, barely distinguishable from the stars around it. The sun itself would appear only about 2/3 the size it does from Earth, casting a dimmer, colder light across the rusty landscape. There would be no bird songs, no wind rustling through trees, no sound of rain, no scent of fresh-cut grass or ocean salt. The Martian environment is utterly alien, a cold, dry, dusty desert stretching to every horizon, painted in shades of rust and ochre beneath a butterscotch sky. Yet despite all these challenges, the question isn't really whether we can go to Mars and come back. We have the technology right now to accomplish this feat. The question is whether we're willing to accept the risks, invest the resources, and commit to the long-term vision required to make it happen. And increasingly, the answer from space agencies around the world seems to be yes. NASA's current plans, developed in collaboration with international partners, aim to send humans to Mars sometime in the late 2030s or early 2040s. These aren't just aspirational dreams. They're backed by concrete hardware development and testing. The Space Launch System, NASA's heavy-lift rocket designed specifically for deep space missions, has already completed its first test flight. The Orion spacecraft, which will carry astronauts on journeys beyond low Earth orbit, has flown multiple test missions. The technologies being developed and tested aboard the International Space Station, life support systems, closed-loop environmental controls, advanced materials, medical countermeasures for long-duration spaceflight, are all stepping stones toward Mars. SpaceX, the private aerospace company founded by Elon Musk, has been even more ambitious in its timelines, though admittedly more flexible with its target dates. The company's Starship vehicle, a fully reusable super heavy-lift launch system, is being designed explicitly for Mars missions. SpaceX has proposed a dramatically different approach to the Mars journey, one that could potentially reduce travel times and change the entire equation of interplanetary travel. Recent research published in early 2026 suggests that using advanced propulsion systems and optimized trajectories, missions aboard vehicles like Starship could potentially reduce the one-way travel time to Mars to as little as 3 months. 3 months instead of 7. That's a massive reduction, cutting the journey time by more than half. This would be achieved through a combination of factors: launching with more fuel, using more powerful engines, and following a faster trajectory that requires more energy but gets you there quicker. Think of it like the difference between taking a leisurely scenic route versus the interstate highway. You're going to the same destination, but one gets you there much faster at the cost of using more fuel. However, and this is crucial, even with these faster transit times, the fundamental problem of orbital mechanics doesn't change. You'd still need to wait on Mars for the planets to align properly for your return journey. The laws of physics don't care how advanced your rocket is. Earth and Mars will still be where they are, moving as they move, governed by the same gravitational equations that have ruled the solar system for billions of years. So even with a 3-month journey each way, you're still looking at a minimum mission duration of approximately 21 months. The faster travel time would primarily benefit the astronauts by reducing their exposure to space radiation during transit and lessening the physiological effects of prolonged weightlessness. There's another approach that's been proposed, though it remains firmly in the realm of theoretical discussion rather than practical planning: the opposition class mission. Instead of waiting on Mars for the optimal return window, a spacecraft could take a much longer route back, swinging far out into the solar system, perhaps even passing near Venus before returning to Earth. This trajectory would be far less efficient, requiring substantially more fuel and taking longer, potentially up to 2 years just for the return leg. The total mission time could stretch to 4 years or more. The advantage? No extended surface stay required. You could limit your time on Mars to just a few weeks or even days. The disadvantage? You'd be spending even more total time in space, with all the radiation exposure and physiological degradation that entails, and you'd need to carry enough supplies for a much longer journey. Most mission planners have concluded this approach makes little sense. If you're going all the way to Mars, you might as well stay for a while and make the journey worthwhile. Let's put all of this into perspective by looking at what we've already accomplished. Every successful Mars mission to date has been robotic. We've sent orbiters, landers, and rovers, but never people. The first successful Mars flyby was NASA's Mariner 4, which zipped past the red planet on July 15, 1965, after a journey of 228 days, about 7.5 months. It returned 21 grainy black-and-white images that revolutionized our understanding of Mars, revealing a cratered, moon-like surface that shattered romantic notions of Martian civilizations. The first successful landing came with Viking 1 on July 20, 1976, exactly 7 years after humans first walked on the Moon. Viking 1's journey took just over 10 months. Its twin, Viking 2, landed in September of the same year. Both landers operated for years, sending back the first color images from the Martian surface and conducting experiments searching for signs of life. The results were ambiguous and remain debated to this day, but they opened the door to decades of Mars exploration that followed. Fast forward to more recent times. The Mars rover's spirit and opportunity, those plucky robotic explorers that captured the world's imagination, each took about 7 months to reach Mars after their launches in 2003. Opportunity, designed for a 90-day mission, operated for nearly 15 years, finally going silent during a planet-wide dust storm in 2018. It traveled over 45 kilometers across the Martian surface, examining rocks, analyzing soil, and peering into craters, all while being controlled by teams on Earth dealing with those minutes-long communication delays. Curiosity, the car-sized rover that's been exploring Crater Gale since 2012, took that 8.5-month journey I mentioned earlier. It's still operating today, climbing the slopes of Mount Sharp and analyzing the geology of Mars layer by layer, reading the planet's history like a book written in stone. And Perseverance, the newest rover which landed in 2021, brought along something unprecedented: a small helicopter named Ingenuity. Ingenuity's story deserves a moment of appreciation. This tiny helicopter, weighing less than 2 kilograms, about 4 pounds, became the first aircraft to achieve powered, controlled flight on another planet. The Martian atmosphere is incredibly thin, remember, making it exceptionally difficult to generate lift. Flying on Mars is equivalent to flying at an altitude of 30 kilometers on Earth, which is about 3 times higher than commercial aircraft cruise. Yet Ingenuity has completed dozens of flights, far exceeding its original 5-flight demonstration mission. It scouts terrain for Perseverance, tests technologies for future missions, and proves that aerial exploration of Mars is possible. Each successful flight is a triumph of engineering and a glimpse of what future human missions might use to explore the red planet more efficiently. All these robotic missions have paved the way for human exploration, answering critical questions about the Martian environment, testing landing technologies, and identifying resources that future astronauts might use. But there's a fundamental difference between sending robots and sending people. Robots don't need to come back. Robots don't need life support. Robots don't complain about the food, don't get homesick, and don't require psychological support. A failed robotic mission is a tragedy for science and a loss of investment, but a failed human mission would be a catastrophe that could set space exploration back by decades. This is why the preparation for human Mars missions is so methodical, so careful, so seemingly slow. Every technology must be tested and retested. Every system must have backups and backups. The stakes couldn't be higher. When those first astronauts launch toward Mars, and they will launch probably within the lifetime of many people watching this video, they'll be embarking on a journey unlike any in human history. The Apollo astronauts who went to the moon were only 3 days from home. If something went catastrophically wrong, they could abort and return to Earth relatively quickly. Mars astronauts won't have that option. Once they're committed to the journey, they're committed for years. So what would a realistic Mars mission timeline actually look like? Let's walk through it step by step, from launch to landing back on Earth. This is based on current mission architectures being studied by NASA and other space agencies, using the best available technology and realistic assumptions about what we can accomplish in the coming decades. Month 0. Launch. The crew departs from Earth during an optimal launch window. This wouldn't be a single rocket launch, but rather a carefully choreographed sequence of launches delivering cargo, fuel, supplies, and finally the crew. Some mission concepts propose sending cargo and equipment ahead on slower, more fuel-efficient trajectories, giving them time to arrive and be verified as operational before the crew even leaves Earth. Imagine stepping into a house where the furniture has already been delivered and set up. That's the idea. The crew's habitat on Mars would already be there, powered up, tested, and ready for occupancy. Months 1 through 7. Transit to Mars. The crew lives aboard their spacecraft, which is both their home and their lifeboat. They maintain systems, conduct scientific observations, exercise rigorously to combat muscle and bone loss, and monitor their own health. They watch Earth shrink behind them and Mars grow larger ahead. Communication delays increase daily. They experience the psychological reality of being farther from home than any human has ever been. At some point during this journey, they cross an invisible threshold where Mars becomes closer than Earth, the point of no return. From that moment on, any emergency means dealing with it themselves or continuing forward to Mars. Going back is no longer the faster option. Month 7. Arrival and landing. This is perhaps the most terrifying part of the entire mission. Landing on Mars is notoriously difficult. The atmosphere is thick enough to create heat during entry, requiring a heat shield, but too thin to allow parachutes alone to slow a spacecraft to a safe landing speed. The combination of atmospheric entry, supersonic parachutes, and powered descent using rockets must work perfectly in a sequence that NASA engineers have called 7 minutes of terror. That's how long it takes from hitting the top of the Martian atmosphere to touchdown, and every second is critical. Remember those communication delays? The crew and mission control can't communicate in real time during landing. By the time mission control sees the spacecraft beginning its descent, it has already either landed successfully or crashed. The crew is truly on their own. Months 8 through 22. Surface operations. Assuming a successful landing, the crew now spends 15 to 18 months on Mars. This is what they came for: the opportunity to explore another planet with human eyes, human hands, and human intuition. They conduct geological surveys, drill for subsurface ice, search for signs of past or present microbial life, test technologies for producing fuel from the Martian atmosphere, grow food in Martian soil supplemented with nutrients from Earth, and document everything they discover. They establish humanity's first foothold on another world. They experience Martian seasons, dust storms, the strange blue sunsets that occur when the sun's light filters through Martian dust. They look up at night and see Earth as a morning or evening star, accompanied by the moon, 2 pale dots of light representing everything humanity has ever known, everyone who has ever lived, all contained in those two tiny specks. This extended surface stay isn't just waiting time, it's the scientific heart of the mission. While rovers like Perseverance are remarkable, they're slow. Perseverance's top speed is about 152 meters per hour, less than 0.1 kilometer per hour. A human geologist can cover more ground in a day than a rover covers in months. Humans can make intuitive decisions, recognize patterns, adapt to unexpected discoveries, and pursue interesting findings in real time. When Apollo astronauts explored the Moon, they accomplished in hours what robotic missions would have taken months to achieve. The same would be true on Mars, only more so because Mars is a far more complex and geologically diverse world than the Moon. During their time on Mars, the crew would also face the daily challenges of living in an environment that's actively trying to kill them. Every excursion outside the habitat requires donning a spacesuit, not the relatively simple pressure suits used for spacewalks near Earth, but sophisticated systems capable of protecting against temperature extremes, providing life support for extended periods, and allowing enough mobility for meaningful work. Martian dust is a particular concern. It's extremely fine, almost like talcum powder, and it's electrostatically charged due to the dry environment and UV radiation. It sticks to everything. It gets into seals, into mechanisms, into fabrics. The Apollo astronauts reported that lunar dust was one of their most persistent problems, and Martian dust is even finer and potentially more troublesome. Some of it contains perchlorates, toxic compounds that could be harmful if inhaled or ingested. Keeping habitats clean and preventing contamination becomes a daily struggle. Water would be one of the most precious resources. While we now know Mars has substantial water ice, particularly at the poles and in subsurface deposits at various latitudes, extracting and purifying it requires energy and equipment. Every drop would be recycled, just like on the International Space Station, but for much longer duration. Drinking water comes from humidity condensed from the air, from purified urine, from moisture extracted from the soil. It sounds unpleasant, but by the time water goes through modern purification systems, it's cleaner than most tap water on Earth. Still, the psychology of it can be challenging. Water for hygiene would be even more limited. Showers, if available at all, would be brief and infrequent. The crew would likely rely on sponge baths and waterless cleansing systems, similar to what astronauts use today on the space station. Food presents another interesting challenge. Carrying 3 years of food for a crew of 6 or 8 people requires a massive amount of supplies, several tons. Some of this can be reduced by growing fresh food on Mars. Research aboard the International Space Station has already demonstrated that plants can grow in space, and experiments with Martian soil simulant here on Earth have shown that with proper amendments, certain crops can thrive. Imagine being on Mars and eating a salad made from lettuce you grew yourself in Martian soil under LED lights, inside a pressurized greenhouse. That fresh food isn't just nutrition, it's psychological sustenance, a living connection to Earth, a splash of green in an endlessly red world. The smell of growing plants, the taste of fresh vegetables after months of packaged food, the simple act of gardening. These things matter more than you might think when you're millions of kilometers from home. Month 23, departure from Mars. The return window opens. The crew loads their samples, carefully selected rocks, soil cores, perhaps atmospheric samples, anything that might contain traces of past or present Martian life, into the ascent vehicle. This is another nail-biting moment. The Mars ascent vehicle must launch successfully, reach orbit, and rendezvous with the return spacecraft waiting above. There's no second chance. If the ascent fails, the crew is stranded on Mars with no possibility of rescue. The Mars ascent vehicle would likely use fuel manufactured on Mars itself, produced from the Martian atmosphere using a chemical process that combines carbon dioxide with hydrogen brought from Earth to create methane and oxygen. This technique, called in situ resource utilization, dramatically reduces the amount of fuel that needs to be transported from Earth, making the entire mission more feasible. Months 24 through 30. Return journey. The crew is going home. Earth is getting closer. The communication delay is shrinking. They can see their home planet growing larger in the windows, changing from a star to a disk, from a disk to a world they can begin to recognize. Continents become visible. Weather patterns swirl across familiar oceans. The psychological relief must be immense, but the journey is still dangerous. Life support systems that have been operating for over 2 years must continue functioning flawlessly. The crew's physical condition, after months in Mars' low gravity followed by months in zero gravity, would be significantly compromised. They'd be weak, their cardiovascular systems deconditioned, their immune systems suppressed. Medical monitoring becomes increasingly important as Earth approaches. Month 30 to 31, Earth approach and landing. The spacecraft must execute a precise entry into Earth's atmosphere. Coming in too steeply means burning up. Too shallow means bouncing off and returning to space. After traveling hundreds of millions of kilometers, the margin for error in these final moments is measured in fractions of a degree. The crew experiences forces they haven't felt in years as atmospheric drag slows them down. Parachutes deploy. Finally, touchdown, on land or in the ocean, depending on the spacecraft design. Recovery teams move in, the hatch opens. For the first time in roughly 3 years, the crew breathes unfiltered air from their home planet. They feel the full weight of Earth's gravity, probably collapsing under their own weight after so long in lower gravity environments. They see the sky, truly blue, not butterscotch. They feel wind, real wind carrying sense of Earth and ocean and life, their home. But their journey isn't quite over. Weeks or months of rehabilitation await them. Their bodies must readapt to Earth's gravity, rebuild muscle and bone, recalibrate cardiovascular systems. Psychological adjustment takes time too. They've experienced something no one else has, seen things no one else has seen, lived through challenges that no one else can fully understand. They carry Mars with them, in their memories, in their samples, in the data they collected, and perhaps in subtle ways we don't yet understand. They are, quite literally, the farthest humans from home who have successfully returned. This entire odyssey, 30 to 36 months from launch to landing, represents one of the greatest challenges humanity has ever undertaken. It makes the Apollo program look like a weekend camping trip by comparison. Apollo 11, from launch to splashdown, lasted just over 8 days. The longest Apollo mission, Apollo 17, lasted 12.5 days. The International Space Station has taught us about long-duration spaceflight, with some astronauts spending nearly a year in orbit, but they're still in low Earth orbit, still close enough that emergency evacuation back to Earth is possible within hours if necessary. Mars is different. Mars is commitment on a scale we've never attempted before. Yet for all the challenges, for all the risks, for all the years away from home, why do we want to go? What drives this ambition to send humans across the solar system to a cold, dry, hostile desert planet? The answers are as varied as the people who dream of Mars, but they all connect to something fundamental about what it means to be human. First, there's the scientific imperative. Mars is the most Earth-like planet in our solar system, and yet it's profoundly different. Billions of years ago, Mars was warmer and wetter. Rivers flowed across its surface, carving valleys that dwarf the Grand Canyon. Lakes, and perhaps even an ocean, filled impact basins. The climate was more hospitable, the atmosphere thicker. We know this from the geological evidence that rovers and orbiters have meticulously documented. But something happened. Mars lost most of its atmosphere, its surface water evaporated or froze into underground ice deposits, and the planet became the frozen desert we see today. Understanding what happened to Mars helps us understand what could happen to Earth. It's a cautionary tale written in rust-colored stone. More tantalizing still is the question of life. Did Mars ever host living organisms during its warmer, wetter past? Could microbial life persist even now in subsurface aquifers or pockets of liquid water beneath the polar ice caps? The question of whether life has ever existed beyond Earth is one of the most profound in all of science. If we find that life arose independently on Mars, it would suggest that life might be common throughout the universe wherever conditions permit. If we find that Mars has always been lifeless, despite having liquid water and other favorable conditions early in its history, that tells us something equally important. Perhaps life is rare, perhaps Earth is special, perhaps we are more alone in the cosmos than we dare to imagine. These questions can't be fully answered by robots, as capable as they are. A human geologist with a rock hammer and trained eyes can investigate more sites in an afternoon than a rover can examine in weeks. Humans can recognize unexpected patterns, follow hunches, adapt to surprising discoveries. When Apollo astronauts discovered orange soil on the Moon during Apollo 17, volcanic glass beads that revolutionized our understanding of lunar volcanism, it was because geologist-astronaut Harrison Schmitt recognized something unusual and pursued it. That kind of intuitive investigation is difficult to program into a robot, especially with minutes-long communication delays. Beyond the science, there's the practical consideration of survival. Earth is our only home right now, and it's a fragile home. We face challenges from climate change, asteroid impacts, pandemics, nuclear weapons, and other existential risks, both natural and human-made. Having a self-sustaining human presence on another world provides a backup for Earth's biosphere and for human civilization. It's not about abandoning Earth. This planet will always be our home, the world that gave birth to our species and nurtured us for hundreds of thousands of years. But it is about ensuring that some catastrophe, whether cosmic or of our own making, doesn't erase everything we are and everything we've built. Carl Sagan called this life insurance for the species, and it's hard to argue with the logic. Then there's the inspiration factor, which skeptics often dismiss, but which may be the most important reason of all. The Apollo program didn't just land humans on the Moon, it transformed human consciousness. It gave us the Earthrise photograph, that iconic image of our blue marble rising over the lunar horizon, which helped spark the environmental movement. It demonstrated what humans could achieve when we set aside our differences and worked toward a common goal. It inspired an entire generation to pursue careers in science, technology, engineering, and mathematics. The average age in mission control during the Apollo 11 landing was just 26 years old. 26. These were young people who had been inspired by earlier space achievements and who then achieved something that still seems impossible more than 50 years later. A human mission to Mars would inspire in ways we can barely imagine. Children watching those first footsteps on Martian soil would grow up knowing that the boundaries of human possibility extend beyond anything previous generations dared to dream. The technologies developed for Mars missions, advanced life support systems, radiation shielding, closed-loop recycling, in-situ resource utilization, artificial intelligence, autonomous systems, would find applications back on Earth, improving life for billions. History shows that space exploration delivers returns on investment many times over, not just in direct applications, but in the expanded human capital of inspired and educated people choosing technical careers. There's also something deeply stirring about the continuity of exploration that a Mars mission represents. For our entire existence as a species, humans have been explorers. We evolved in Africa and then spread across the entire planet, crossing mountains and deserts, sailing vast oceans, eventually reaching every continent and every isolated island. Exploration is encoded in our DNA, written into our psychology, the same curiosity that led our ancestors to wonder what lay beyond the next valley, beyond the horizon, beyond the edge of the known world, now leads us to wonder what lies beyond our planet. Going to Mars is the next chapter in an ancient story, the story of a curious species that looks at distant places and asks, "What's there? Can we reach it? What might we learn?" Now let's address something crucial that often gets overlooked in discussions about Mars missions, the sheer difficulty of the engineering challenges involved. We've been talking about timelines and distances, but the technical problems that must be solved are staggering in their complexity. Getting to Mars and back safely requires breakthroughs and refinements across dozens of different fields. Propulsion is the most obvious challenge. Current chemical rockets, the kind we've been using since the dawn of spaceflight, work well enough to get us to Mars, but they're inefficient for the enormous distances and payloads involved. They require vast amounts of fuel, which adds weight, which requires more fuel in a vicious cycle. Advanced propulsion concepts are being explored. Nuclear thermal propulsion, where a nuclear reactor heats propellant to extremely high temperatures before expelling it for thrust, could cut travel times significantly while using less fuel. Ion drives, which accelerate particles to extremely high velocities using electric fields, provide very efficient but low-thrust propulsion suitable for cargo missions. Solar electric propulsion uses electricity from solar panels to power ion engines. Each technology has advantages and drawbacks, and deciding which to use involves complex trade-offs between speed, efficiency, reliability, and cost. Life support systems present another enormous challenge. On the International Space Station, supplies are regularly replenished from Earth. Water and oxygen are partially recycled, but the station still depends on regular cargo deliveries. For a Mars mission, that's impossible. Everything must be carried from the start or produced along the way. The environmental control and life support system must recycle water with near-perfect efficiency, extracting it from humidity, urine, and even the moisture in the crew's breath. Oxygen must be generated from water through electrolysis, or extracted from carbon dioxide using chemical processes. Carbon dioxide exhaled by the crew must be scrubbed from the air and either vented or converted back into oxygen. Trace contaminants, the off-gassing from materials, the biological byproducts of human metabolism, the inevitable accumulation of chemicals in a closed environment, must be monitored and removed. The system must function flawlessly for years with minimal maintenance because there's no calling for a repair technician when you're on the way to Mars. Radiation shielding is perhaps the most intractable problem. Traditional shielding, thick layers of lead or other dense materials, is too heavy to be practical for spacecraft. Water provides good radiation protection and serves a dual purpose, so mission designs often incorporate water storage tanks positioned in the spacecraft walls. Polyethylene, a hydrogen-rich plastic, is surprisingly effective at blocking radiation and much lighter than metal. Some designs propose using the crew's food supplies, waste products, and other materials as makeshift shielding, arranging them around a storm shelter where the crew would retreat during solar particle events, dangerous bursts of radiation from solar flares that can occur with little warning. But there's a limit to how much protection passive shielding can provide without making the spacecraft impossibly heavy. Active shielding concepts are being researched, generating magnetic fields around the spacecraft to deflect charged particles, similar to how Earth's magnetosphere protects us. This remains highly experimental. The power requirements are substantial and the technical challenges are immense. For now, crews will simply have to accept elevated radiation exposure as part of the mission risk profile. It's sobering to realize that the astronauts who first travel to Mars will be accepting long-term health risks that we can calculate but cannot entirely prevent. Landing systems for Mars are another engineering puzzle that still doesn't have a perfect solution. Mars's atmosphere is a terrible compromise, thick enough that you need heat shields and have to deal with atmospheric heating during entry, but too thin for parachutes to slow you down adequately. The Apollo lunar landers could descend using rockets alone because the Moon has no atmosphere. Mars landers need a combination of heat shields, supersonic parachutes, and finally, powered descent using rockets, a complex sequence where any single failure means catastrophe. Now scale that up from rovers weighing hundreds of kilograms to human landers that might weigh 20, 30, or even 50 metric tons. The Perseverance rover, which weighed just over 1,000 kilograms, required the innovative Sky Crane system, a hovering rocket platform that lowered the rover on cables like some kind of spacecraft yo-yo. It worked brilliantly, but scaling that system up to human-carrying vehicles presents enormous challenges. SpaceX's approach with Starship is characteristically audacious. Land the entire vehicle vertically on its rockets, the same way it would land back on Earth. This requires enough propellant to slow down from hypersonic speeds in the thin Martian atmosphere and perform a powered landing, a maneuver that consumes significant fuel. But if it works, it provides a reusable system that could revolutionize Mars access. Of course, it has to work. The first few landings on Mars using any new system will be moments of extreme tension for everyone involved. Then there's the Mars Ascent Vehicle, which must launch from the Martian surface and reach orbit to rendezvous with the return spacecraft. This might seem straightforward. After all, we've been launching rockets for decades, but consider that no rocket has ever launched from Mars. The vehicle must sit on the surface for 15 to 18 months, exposed to temperature extremes, dust storms, and intense UV radiation, then work perfectly on its first and only attempt. There are no second chances. The propellant, likely manufactured on Mars from atmospheric carbon dioxide, must remain stable and usable after months of storage. The engines must ignite reliably in an environment they've never been tested in. The guidance systems must work flawlessly to achieve orbital rendezvous with the return vehicle. It's a tall order. Medical capabilities for a Mars mission must be far more sophisticated than anything we currently have in space. On the International Space Station, if a medical emergency occurs, the crew can be back on Earth within hours. Mars astronauts won't have that option. They need to be able to handle everything from minor injuries to potentially life-threatening emergencies with only the medical equipment and expertise available on board. This means the crew must include someone with extensive medical training, ideally a physician with surgical experience, and the spacecraft must carry diagnostic equipment, surgical tools, medications, and supplies adequate for any foreseeable medical contingency. Imagine the psychological weight of being the crew medical officer, knowing that you might have to perform emergency surgery on a crewmate in microgravity or in Mars's low gravity, with no possibility of consultation with specialists on Earth in real time, with limited equipment, and with the knowledge that your patient's life depends entirely on your skills. Medical simulations and training can prepare someone for many scenarios, but the reality of cutting into a colleague's abdomen to address internal bleeding or performing emergency dentistry when someone breaks a tooth would test anyone's composure. Psychological support becomes equally critical. 3 years is a long time to maintain mental health in isolation and confinement. The crew selection process would need to identify individuals who are not only technically competent, but also psychologically resilient, socially compatible, and emotionally stable. Even then, problems can arise. Past experience with Antarctic research stations, submarines, and long-duration space missions shows that even carefully selected crews can develop conflicts, experience mood problems, or suffer from anxiety and depression under prolonged stress and isolation. Mission planners are considering various countermeasures. Careful habitat design with private spaces for each crew member, areas for exercise and recreation, and perhaps even viewports or high-resolution screens showing natural Earth scenes could help. Regular communication with family and friends, despite the time delays, provides emotional connection to home. Structured schedules with varied activities prevent monotony. Some proposals include virtual reality systems that could allow crew members to visit Earth environments, walking through forests, standing on beaches, exploring cities, as a form of psychological escape from the confined spacecraft or habitat. The composition of the crew matters enormously. Early Mars missions will likely include a mix of nationalities, reflecting the international cooperation required for such an ambitious endeavor. Having crew members from different cultures and backgrounds brings diversity of perspective and problem-solving approaches, but it also requires careful attention to cultural sensitivities and communication styles. The crew will need to function as a cohesive unit despite differences in language, customs, and worldviews. In many ways, they would represent humanity as a whole, not just one nation or culture, but our entire species taking its first steps toward becoming a multi-planet civilization. Let's consider the economics for a moment, because nothing this ambitious happens without substantial financial investment. NASA's estimates for a human Mars mission program range from several hundred billion to possibly over $1 trillion when all the development costs, hardware, testing, and operations are included. That's an enormous sum, and it's often the target of criticism. Why spend such vast resources on Mars when we have problems here on Earth? Poverty, disease, environmental degradation, crumbling infrastructure? It's a fair question, and it deserves a thoughtful answer. First, the money spent on space exploration doesn't vanish into the void. It's spent here on Earth, employing scientists, engineers, technicians, and countless support personnel. It drives technological innovation that spills over into other sectors. Second, the actual percentage of government budgets dedicated to space exploration is tiny. NASA's current budget is less than half of 1% of the United States federal budget. For context, Americans spend more on pizza annually than NASA receives in funding. We're not choosing between Mars and solving Earth's problems. We can do both. In fact, we must do both. Moreover, the technologies developed for Mars missions directly address Earth challenges. Closed-loop life support systems are essentially advanced sustainability technologies, maximizing resource efficiency and minimizing waste. Exactly what we need for a more sustainable civilization here on Earth. Water purification technologies developed for space-find applications in areas lacking clean water, energy-efficient systems, advanced materials, improved medical technologies. All these Mars mission spin-offs benefit everyone. There's also the economic multiplier effect. Studies of the Apollo program showed that every dollar invested returned $7 to $14 to the economy through new technologies, industries, and the education of skilled workforce. There's every reason to expect similar or better returns from a Mars program. The development of reusable rocket systems alone, driven partly by Mars mission requirements, is already revolutionizing space access and creating new economic opportunities in satellite deployment, space tourism, orbital manufacturing, and space resource utilization. Several nations and organizations are now seriously planning for Mars. NASA remains a leader, with its Artemis program aiming to establish a sustainable presence on the Moon as a stepping stone to Mars. The European Space Agency is developing technologies and participating in international Mars mission planning. China has expressed ambitions to send humans to Mars, having already successfully landed rovers on the Martian surface. The United Arab Emirates is investing heavily in Mars science and technology. India has operated successful Mars orbiters. Russia, despite economic challenges, maintains Mars ambitions rooted in its proud history of space achievement. Japan, Canada, and other spacefaring nations are contributing technologies and expertise. The international nature of Mars exploration is itself significant. Space exploration, particularly human spaceflight, has historically brought together nations that might otherwise be adversaries. The International Space Station is perhaps the best example, a platform where astronauts and cosmonauts from the United States, Russia, Europe, Japan, and Canada live and work together in orbit, maintaining cooperation even when tensions rise on Earth below. A Mars mission would likely require even greater international cooperation, pooling resources, expertise, and technologies from across the globe. In a world often divided by politics, religion, and ideology, working together to accomplish something no single nation could achieve alone has profound symbolic and practical importance. Then there's the private sector. SpaceX, as mentioned, is developing Starship explicitly for Mars missions, with founder Elon Musk openly stating that the company's ultimate goal is to make humanity a multi-planetary species. Blue Origin, founded by Jeff Bezos, focuses more on near-Earth infrastructure but develops technologies applicable to Mars missions. Other companies are working on life support systems, habitats, power generation, in-situ resource utilization, and countless other pieces of the Mars mission puzzle. The emergence of a commercial space industry changes the equation significantly, potentially reducing costs through innovation and competition while increasing the pace of development. Some critics argue that we should send robots instead of humans. Cheaper, safer, no risk of death, and increasingly capable. It's true that robotic exploration will continue to play a vital role, and for some tasks, robots are simply better suited than humans. But there's something robots can't replicate: the human experience, the human perspective, the transformative effect of having been there. When humans first stepped on the moon, the world watched in collective amazement. When robots land on Mars, it's interesting news for a day or two, then fades from public consciousness. Human missions capture imagination in ways that robotic missions simply don't, and that inspiration, that sense of shared achievement and expanded possibility, has value that's difficult to quantify but very real. Furthermore, if our long-term goal is to establish a human presence beyond Earth, we must learn how to send humans beyond Earth. We need to understand how people adapt to long-duration spaceflight, how to keep them healthy and productive, how to create sustainable habitats on other worlds. These are lessons we can't learn by sending robots alone. At some point, we have to take the leap. Mars is the logical first destination, close enough to be reachable with current technology, far enough to present real challenges, and interesting enough to justify the effort and risk. What happens after that first mission? If all goes well, if the crew returns safely with samples and data and stories that captivate the world, what comes next? The answer, almost certainly, is more missions. One successful Mars landing doesn't establish a human presence any more than Apollo 11 made us a moon-faring civilization. We landed on the moon 6 times between 1969 and 1972, then didn't return for more than 5 decades. That's not how you build a sustainable presence beyond Earth. Future Mars missions would likely follow in relatively quick succession, perhaps every 26 months as launch windows open. Each mission would build on the previous one, establishing more infrastructure, conducting deeper exploration, and eventually creating a permanent base. This Mars base would start small, perhaps just a few connected habitats supporting half a dozen people. Over time, it would grow. More habitats would be added. Greenhouses would expand food production capacity. Manufacturing facilities would begin producing tools, spare parts, and construction materials from Martian resources rather than bringing everything from Earth. The base would gradually become more self-sufficient, less dependent on supply missions from Earth. Eventually, we might see something remarkable: the first human born on Mars. A Mars native who experiences their home planet's lower gravity from birth, whose body develops in 0.38 Earth gravity, who grows up seeing 2 small moons in the butterscotch sky, for whom Earth is an abstract concept, a beautiful blue star that their parents came from, but not home, not their home. Mars is their home. That moment, whenever it comes, will mark a fundamental transition in human history. The point at which humanity truly becomes a multi-world species. But I'm getting ahead of myself. We're talking about events decades or centuries in the future. The question you asked was simpler. How long does it take to get to Mars and come back? And now, after this long journey through orbital mechanics, mission planning, technological challenges, and the broader context of human Mars exploration, you know the answer. The minimum round-trip time, assuming optimal trajectories and launch windows, is approximately 21 to 24 months. More realistically, with appropriate safety margins and mission objectives, we're looking at 30 to 36 months, 2.5 to 3 years. That breaks down to roughly 7 months traveling to Mars, 15 to 18 months on the surface waiting for the return window while conducting exploration and science, then another 7 months traveling back to Earth. Could we go faster? Possibly. Advanced propulsion technologies might shave months off each leg of the journey. Could we go slower? Sure, by choosing less optimal trajectories or staying longer on Mars, the mission could stretch to 4 years or more. But the core constraint remains unchanged: the dance of planetary orbits that governs when we can leave and when we can return. These timeframes have profound implications for everything about a Mars mission. They determine how much food and water must be carried or produced. They dictate how reliable every system must be, Not for days or weeks, but for years of continuous operation without failure. They shape the psychological profile required of crew members who must cope with isolation, confinement, and danger for longer than most people stay in a single job or apartment. They influence the medical capabilities required, the radiation exposure accumulated, the physical deconditioning that occurs despite countermeasures. 3 years. 1,000 days. It's longer than World War I lasted. It's about how long it takes to earn a bachelor's degree. It's the age when children first begin forming long-term memories. It's a significant fraction of a human lifetime, substantial enough that astronauts departing for Mars in the prime of their careers would return noticeably older, having sacrificed years of their lives for humanity's first steps toward becoming an interplanetary civilization. And yet, despite the challenges, despite the risks, despite the years away from everything and everyone they know, there will be no shortage of volunteers. When NASA, SpaceX, or any other organization announces crew selection for the first Mars mission, applications will number in the hundreds of thousands, because there are people, rare, exceptional people, who look at those 3 years not as sacrifice, but as opportunity. The opportunity to be first, to explore, to discover, to represent humanity in taking one of the most significant steps in our species' history. The journey to Mars and back isn't just a technical achievement, though it certainly is that. It's not just a scientific mission, though the science will be invaluable. It's a statement about who we are and who we aspire to be. It says that we're not content to remain on one world forever. It says that we can overcome seemingly impossible challenges when we work together. It says that the horizon of human possibility extends beyond anything previous generations imagined. When that first crew launches toward Mars, and they will launch, probably sooner than many people expect, they'll be carrying with them the dreams of everyone who has ever looked up at that red point of light in the night sky and wondered. They'll be following in the footsteps of explorers throughout human history who ventured into unknown territories, driven by curiosity and courage. And when they return, 2.5 or 3 years later, they'll bring back not just rock samples and scientific data, but something more precious, proof that the next chapter of human civilization has begun. So, there's your answer. Getting to Mars and back takes approximately 30 to 36 months, 2.5 to 3 years of your life, minimum. It's a long time, but for the first humans to walk on another planet, to stand beneath an alien sky and look back at Earth as a pale blue dot suspended in the darkness, to take humanity's first steps toward becoming a spacefaring civilization, it might just be the greatest 3 years anyone has ever spent. If you found this journey through the challenges of reaching Mars fascinating, you'll definitely want to check out my previous video exploring another incredible space challenge, why going back to the moon is harder than the first time. We dive deep into why returning to the lunar surface decades after Apollo presents unique obstacles that even our advanced technology struggles to overcome. It's a perfect companion to today's Mars discussion, and I think you'll find it just as eye-opening. The video is right here on screen and pinned on the comments. Thanks for watching, and I'll see you in the next one.